Hi, my name is Kritesh Nam, matrix number 225380. Today I'm going to be presenting on my fluid mechanics assignment 1, which is titled Fluid Mechanics and Dimensional Analysis. So before we go in deep in our today's topic, first we must know the contents that will be covered in my presentation today. So the contents that will be covered in my presentation is the introduction in fluids, fluid features, dimensional analysis, and conclusion. So, firstly, what is fluid mechanics? The study of fluid behavior, whether at rest or in motion, is known as fluid mechanics. So, if it's related to rest, it means static fluid. If it's related to motion, it means fluid dynamics. So, the physical characteristics of fluids, such as density, specific weight, specific gravity, surface tension, and viscosity, can determine whether they are solids or gases. So it is important to use units of measurements carefully when doing quantitative analysis of fluid systems. There, there is use of both the US gravitational system and SI metric unit in fluid mechanics. So next we move on to fluid features. There are plenty of fluid features that will be covered in my presentation today. So the first fluid feature is surface tension, followed by pressure, specific weight, density, specific gravity, compressibility, and viscosity. So as I mentioned, the first fluid feature that I'm going to be talk about today is density. So the density of a fluid is defined as the ratio of mass of the fluid to its volume. The density of gases is independent on pressure and temperature, while the density of liquid remains constant. So density of gas can be negligible. Meanwhile, density of liquid can be calculated by using the formula density is equals to mass over volume. So the letter rho represents density, while m represents mass, and v represents volume. So the SI unit for density is kilograms per meter cube. So the next fluid feature that I'll be talking about is specific gravity. The specific gravity of a fluid, designated as Sg, is defined as the ratio of density of a fluid to the density of water at some specified temperature. The temperature that is specified is usually taken at 4 Celsius, and at this temperature the density of water is 1000 kilograms per meter cube. So that is why we use the Sg reference point as 4 Celsius. So Sg's formula is basically density of substance over density of water. So the reason why we use 4 Celsius is because the density of water at 4 Celsius is 100 kilograms per meter cube. So thus the density of another substance can be calculated easily because the density of water is a constant value, which is 1000. So next we can move on to specific weight. Specific weight, sometimes referred to as unit weight, is simply the weight of fluid per volume. So specific weight's formula is equals to pressure times gravitational acceleration. Specific weight is really important in fluid mechanics because most of our fluid mechanics calculations require specific weight values. So for example, the questions will give the value of Sg of certain substance. So we need to identify the specific weight of the substance. So in order to do that, we can do that by multiplying the pressure times the gravitational acceleration. So its units in the English system and SI system are lb or feet cube and Newton per meter cube or kilograms per meter square dot second square. Okay, next we move on to compressibility. Compressibility is a measure of how much a substance volume changes in response to fluid changes. It's the relative change in volume of a fluid or solid when placed under pressure. For example, if the pressure increases, the volume decreases. As we may know, we are physics students, so we should know that. Compressibility is directly proportional to strain caused by stress. So the formula is E is equals to E represents compressibility is equals to change in pressure over change in volume over volume. So we can prove by using the compressibility formula that when pressure increases, the volume decreases. So pressure and volume are both inversely proportional of each other. So next we can move on to the next fluid feature, which is pressure. Fluid pressure refers to a measurement of the force per unit area that acts on an object in the fluid or on a closed container surface. Furthermore, the cause of this pressure is due to the acceleration, gravity, or by forces that are outside the closed container. So the simple formula for pressure is equal to force over area. So the force acting on the object over the total area of the object. From that we can find the formula for pressure. So the SI unit for pressure is basically Pascal, which is equals to Newton per meter square. In the English system of units, pressure is expressed as pound per square inch PSI or lbf per inch. So these units depends on which unit we use on our calculations. If for example, if I tend to use calculation in meter cube, so the answer I will get is in Pascal. So for example, if I use my calculation in inches, maybe my answer will be in the English system, which is PSI unit. So next we move on to the final fluid feature, which is surface tension. Surface tension is the tendency of a liquid surface to shrink into the smallest possible area. It occurs when a liquid comes into contact with another phase such as air, and the liquid molecules are attracted to each other than to the other molecules in other phase. The surface of the liquid behaves like an elastic sheet with an inward force of the surface molecules causing the liquid to contract, and a tangential force parallel to the surface of the liquid. The tangential force is generally referred to as surface tension. So surface tension is basically a layer of attraction force that acts on the surface of any liquid, for example water surface tension. So this tension acts as a strong shield that prevents substances from penetrating over the layer. So surface tension exists in all kind of molecules. So surface tension's simple formula is basically just work over area, and the unit for surface tension is basically Newton per meter. So now we will go on to our final fluid feature, which is viscosity. In fluid mechanics, viscosity is a measure of fluid's resistance to flow or its internal friction. It's often referred to as the thickness of fluid. For example, water has low viscosity while honey has high viscosity. Viscosity denotes the opposition to flow. Motor oil, for example, has high viscosity and its resistance to shear is cohesive and it feels sticky, whereas gasoline has low viscosity. The friction forces in flowing fluid result from the cohesion and the momentum interchange between molecules. So viscosity, in simple terms, we can put it as friction. So viscosity prevents the flow of substance in a liquid. So for example, if a substance has high viscosity, that means it can't, as any substance can't flow into it easily. For example, if there's a substance with very low viscosity, for example water, which is low in way, substance can flow directly into it easily. So that means the substance is low viscosity. So for example, honey is very thick and dense, so it has high viscosity, so it prevents flow of substances. So next we can move on to my second part of my presentation, which is on dimensional analysis. Okay, the introduction to dimensional analysis. Dimensional analysis is a mathematical technique making use of study of dimensions. It deals with the dimensions of physical quantities involved in the phenomenon. All physical quantities are measured by comparison, which is made with respect to an arbitrary fixed value. In fluid mechanics, dimensional analysis is performed to obtain dimensional pi terms or groups. According to the principle of dimensional analysis, any prototype can be described by a series of terms or groups that describe the behavior of a system. So dimensional analysis is pretty much necessary in every field of study, and most importantly for fluid mechanics, because the dimension is plays an important role in our calculations, because each dimension has their own specific value, so it plays a very important role in our calculations. So, types of dimensions. So, dimensions can be divided to two types. The first type that I'll be covering is on fundamental dimension. In fluid mechanics, the primary or fundamental dimensions are together with the SI units. So, in fluid mechanics, there are four main dimensions that it is necessary. First one is mass, which is the symbol is M, unit kilogram kg. Second one is length, symbol L, unit is meter M. Third one is time, unit T and seconds S. And the final one is temperature with theta, Kelvin, K. Okay. In other areas of physics, additional dimensions may be necessary. The complete set of specified by the SI system consists of the below: electric current I, ampere; luminous intensity C, candela; amount of substance and mole. So the fundamental dimensions are basically the most basic dimensions that are involved in any calculations. So next, we move on to derived dimensions. In fluid mechanics, the secondary or derived dimensions are quantities that possess more than one type of dimension. So derived dimensions are basically combinations of either multiplication or division of our fundamental dimensions. For example, volume. Volume is basically the fundamental dimension, which is length multiplied three times. So volume is just meter cube. So it's basically fundamental dimension, which is length times length times length. So we get L to the power 3. So that is an example of derived dimension. So these are the properties of derived dimension and the examples. So next, we can move on to the methodology of dimensional analysis. The basic principle of dimensional homogeneity, which means the dimension of each term in an equation on both sides are equal. So dimensional homogeneity, basically in simple terms, it means left hand side is equals to right hand side. The dimension of the left hand side must be equals to the dimension of right hand side. That is the meaning of dimensional homogeneity. So an equation in which dimension of each terms on both sides are the same is known as dimensionally homogeneous equation. Such equations are independent of the system of units. For example, I have an example here. Let's consider the equation V equals to bracket 2gh to the power 1 over 2. So dimension of left hand side is basically LT to the power -1. Dimension to the right hand side is LT to the power -1. So dimension to the left hand side and dimension to the right hand side is the same. So that means the equation V equals to 2gh to the power 1 over 2 is dimensionally homogeneous equation. So next, we move on to the methods of dimensional analysis. So there are basically two methods for dimensional analysis. First one is Rayleigh's method. So Rayleigh's method is used to find the expression for a dependent variable which depends on other variables that relieves a maximum of 3 to 4 independent variables. The method becomes difficult to use if there are more than 4 independent variables. X is an independent variable and x1, x2, x3 are independent variables. According to Rayleigh's method, the relationship between these variables can be expressed as x equals to a certain function, which can be written as x equals to k function x1a and so on. So a, b, c are arbitrary powers which are obtained by comparing the values of fundamental dimensions. So Rayleigh's method, in my opinion, isn't recommended that much because it can be difficult to use if there are more than 4 variables. So I would say it isn't that well suitable to be used. So meanwhile, the second method, which is Buckingham's pi symbol, is the second method that I would suggest. So since Rayleigh's method becomes difficult if there are more variables, so the difficulty to overcome this method is by using Buckingham's pi theorem, which states that if there are n number of variables, independent, dependent physical phenomena, and if the variables contain m fundamental dimensions, then the variables are arranged into n dash m dimensionless terms, which are called as pi terms. So like x1, x2, x3, x4, and so on are the variables involved in the physical formula. Let x be the dependent variable and x2, x3, x4, and xn as the independent variables on which x1 depends. Mathematically, it can be written as x equals to that, which can be written x f1 equals to 0. Ab- the above equation is dimensionally homogeneous. It is because it contains n variables, and if they are m fundamental terms, then it can be written in terms of dimensions groups called pi terms, which are equal to m dash n. Since f1 is equals to pi 1, pi 2, pi 3 is equals to 0, so I could say this is an easier method to prove dimensional analysis. So next we can move on to the property of pi terms. Each pi term is dimensionless and is independent of system of units. Division or multiplication by a constant does not change the character of pi terms. So pi terms is basically just dimensionless property. So it's an easy calculation to use. So each pi term contains m plus 1 variables, where m is the number of fundamental dimensions and also called as repeating variables. Let in the both case x1, x2 and repeating variables, and if the fundamental dimension m equals to 3, then each pi term is written as pi is equals to x1e, x2b, x3c and so on. So pi term, Buckingham's pi term is, I would say, compared to Rayleigh's method, it's a more favorable method in determining the dimension of a system or property. So next I have an example that explains in detail about Rayleigh's and Buckingham's method. So this is an example of a question. So the first step to, okay, let me read out the question. Obtain an expression in non-dimensional form for the pressure gradient in a horizontal pipe of a circular cross-section. Show how this relates to the expression of frictional head loss. So the first step. Step 1. Identify the relevant variables. So the relevant variables that I have in my expression is dp over dx, pressure, volume, d, k, and mu. Write down the dimensions. So I have to list down the dimensions for each one. So for dp over dx, the dimension is ml92 t92. So third step. Establish the number of independent dimension and non-dimensional groups. So the number of relevant variables, we have 6 based on our listing out, we have 6, and the number of independent dimension, we have 3. Independent dimension are like basically fundamental dimensions. So the independent dimensions that I have here are m, l, and t. And number of non-dimensional groups, we have 3 also, which is basically n minus m. We have 3. So step 4. Choose m is equals to 3 dimensional independent scaling variables. Example, geometric D, kinematic time dependent B, dynamic mass dependent P. Okay, next create the pies by non-dimensioning the remaining variables dp over dx, k and u. So pi 1 is equals to dp over dx, dA, dB, pc. Considering dimension on both sides, we have to consider the dimensions for both sides and equate the powers of primary dimensions. Since m only appears in P and T only appears in V, it is easy to deal with this kind first. So from that we get m, the value for arbitrary power for m, which is C, we get -1. The value for arbitrary power for T, which is B, we get -2. The value for arbitrary power for L, which is A, we get -1. So from that we have our equation d over dp over dx is over p over v square. And now we can carry on the step for pi 2, and we can get our dimension again for m, l and t, the arbitrary questions. Then step 6, set out the non-dimensional relationship between pi 1 and the pi 2, pi 3 and so on that we found. So set the function so that it is dimensionless. Okay, next we move on to step 7, which is rearranging for convenience. We may replace any pi by a power of that pi or the product with another pi's, provided with a certain same number of independent dimensional groups. Here we recognize pi as the reciprocal of the Rayleigh's number, so it is more natural to use pi 3 is equal to pi 3 negative 1. So by using this step, we can get a relationship more easily. So we can solve by using Rayleigh's number in Buckingham's pi constant to solve the equation, and thus we can determine the dimension for every single constant in this problem. So that's about it from my presentation on fluid mechanics and dimensional analysis. I would like to say thank you very much for everyone that is listening to this presentation. Thank you. Have a good day.